Okay, you guys. Hey, it's chapter 2, the Earth in space, space. I always want to say like that with a little echo. It makes me feel like I'm floating out there in the a bit in the a beyond area. But we really are. We're a giant spaceship that's cruising at incredible speed through our solar system, and it's just spaceship Earth, man. So what we're going to do is talk about Earth, kind of how it got here, what it's like, the different zones, how we know about what's going on, and the use of seismic waves when that happens, or to investigate our world. Then we're going to talk about some really cool things like our magnetosphere, which is around the outside of the Earth and through it, and then talk about Newton's laws of gravitation. So, very excited, just looking forward to it. So we'll just jump right in. So, one, we are we're a unique planet. We are a unbelievably awesome Goldilocks, and I use Goldilocks because I think of Goldilocks and the Three Bears, and think about if you think about Goldilocks, this bed was too hard, this bed was too soft, but this bed's just right, or this porridge is too hot, and this one's too cold, but this one is just right. Well, we are that Goldilocks. We're a Goldilocks planet, and if you think about it, we're just far enough away from the sun that we don't get too cold or too hot. We're just right, and we're just the right enough size to keep our moon in orbit. And uh, we really are a Goldilocks, and it's very exciting. So if we think about our Earth, if we talk about circumference, going around the Earth, we're about 40,007 kilometers. At the equator, 40,074, not that much different. But if you think about what it really is we're what's called an oblate spheroid, and the oblate spheroid is basically that we're kind of squashed a little bit. And actually, that's not true either. We're a little bit fatter at the bottom than we are at the top, but for more kind of like pear shaped than anything. But we're an oblate spheroid, so we're a little bit wider around the middle. And so when we think about our planet, we have this imaginary line through it called our axis, and that's where we're supposedly spinning around. And if we look at the diameter of the Earth, we're about 12,735 kilometers. Now, what makes us unique is that we are, really, we should have been called Water World. We're 71, 72% water. And if you think about where all the water is, where is our water? Well, we think about if all the water in the world, out of 100%, 96.5 is in the ocean. And that's a lot of water. Now, in the grand scheme of things, the size of the world, it's only a thin film around the outside. But most of our planet's surface area is water. And of that, all that water that's there, about 2.5% is fresh water. Where do we find that fresh water? Well, about half of that fresh water, let's say it's 3%. So 1.5% is locked up in our ice caps and our glaciers, and that's melting. It's reducing. And we think about all of that water, where is it going? That 1.5% that's left, that's all we have that's left for us to consume. But that's all that's left that's really as a liquid form on the planet. So that's lakes, rivers, streams, ponds. And then we talk about our atmosphere, right? And if you think about it, all the water present today on Earth has always been all the water that's present on Earth even way back before the dinosaurs. Now, granted, elementally, there's been some more and some less, but if you think about it, we've been recycling our water on our Earth for quite some time. And so 97% in the oceans, 2% is frozen in polar ice caps and glacier, 1% is groundwater. That still leaves about 1 trillion gallons apiece for us. What's the problem then? Well, it's not equal everywhere. And so if you think about our atmosphere is kind of similar, right? We always go, oh, I'm breathing oxygen. Well, no, you're breathing 21% oxygen, 78% nitrogen, right? And you've got 1% left for all of the gases in the world. 1%. That's incredibly small when we think about it. If we didn't have that nitrogen and we're breathing nitrogen, we breathe pure oxygen, we wouldn't make it. If we had less oxygen, it gets more difficult, obviously. The less oxygen you have, the worse off it gets, right? And so we're just right. We're a Goldilocks. If we think about the interior, how do we know what's inside of our Earth? It's real simple. We started figuring out what was inside of our Earth because of seismic waves. And so when we look at the zones, we'll start with the crust. Now we're going from the outside in. We're coming from outside, going all the way to the center. So our first zone is our crust. Now we have two types of crust, obviously. We have oceanic crust, which is under the ocean, and we have continental crust, which is on the continents. Makes sense, right? And so if you think about the thickness of the various crusts, oceanic crust is thinner at 5 to 10 kilometers thick. Dry land, a little bit thicker, 15 to 80 kilometers thick. Underneath the crust is the mantle. Now, the mantle is made up of actually two different regions, really, the lithosphere and the asthenosphere. Now, and again, we're drilling down and we're going in, but the lithosphere, it's solid. It doesn't want to move, but it does break, right? And then we look at the asthenosphere. The asthenosphere is when we have so much pressure, so much heat in the rock that it actually gets to be the consistency of like toothpaste. And we call that plasticity. Plasticity, the ability for rock to flow and move, but it's not magma. Difference between lava and magma? Magma's under the ground, lava's on top. Good job. So we look at this picture, right? Look at this great big U. We're going to talk about what those are called later. But you see this big U in this rock. Look at this little card on here. Beep, beep. And you've got this U. What happened? Well, the law of superposition says that land is put down like a cake in flat layers. If you have a multi-layer cake, then you have the oldest layer, which is the first layer, on the bottom. So it stands to reason that this rock down here is much older than this rock up here. Okay, great. But what happened here? We had this giant accordion push this together. This was in the mantle. This was deep in the lithosphere. And it caused it to create this U. It pushed it together. All right, so now we're going from the mantle to the outer core. The outer core, right? So it's liquid. It's dense. We know it's predominantly iron, or we believe so. Now, we also think there's some nickel in there. I'll tell you about that in a little bit. Inner core, dense and solid. It's iron and nickel. And what we see is we're learning because of seismic waves what's there, because we know what happens when a seismic wave hits a liquid area and hits a solid area. And so our core makes up about 1/3 of the Earth. All right, so how do we study it? We use waves. Our first one, or our P waves, our primary waves, P, primary, they'll travel through a liquid, solid, and a gas, no problem. And so we can see them as these waves go through our crust. A seismic event on one side of the planet has the ability to travel through the entire planet and be felt on the other side. S waves are the secondary waves. travel only through solids. And so what we're able to do is compare the P and the S waves at where they're located on the globe, and where we see a area that we do not see S waves or a shadow zone, we're able to know where the particular places that we have solid and liquid parts of our Earth. And so real quickly, our outer core stands out. The MOHO is a boundary that's between the crust and the mantle, and it's named for Andrija Mohorovic. It is a layer that is between those two areas. What I'd like you to do is watch the National Geographic's Earthquakes 101. I'll pause right here and then we'll restart. Okay, we're back. Hopefully you enjoyed Earthquakes 101, Nat Geo, very cool. Again, it really had a lot of great information in there. And so when we study seismic waves, we're looking for shadow zones. Shadow zones are what tells us what we're missing. And we can study the shadow zones by simply recording our different earthquakes. Now, what I would like you to do is I'd like you to watch Seismic Shadow Zones Introduction. It gives a good explanation on P and S wave and how using shadow zones, we are able to detect the different parts of the Earth. I'll have you pause right here, and when you're done, we'll see you when you get back. All right, great job. You're back. Exciting. Seismic shadow zones. Very cool. Okay. This is what our Earth would look like if we were to have an earthquake at epicenter of 0 degrees. And so we are able to see the different shadow zones. The P wave shadow zone, we can see where we have the seismic waves reflecting off of the outer core, right? Because it's liquid. Okay. So our Earth has a magnetic field. And essentially we have a north and a south pole. Now, ironically, the north and south pole is actually not exactly where the axis of our Earth is. In other words, it's off just a little bit. And we think that this flips every once in a while, north to south. So again, we have two magnetic poles. The magnetosphere is this area of space where we have this magnetic field, and this magnetic field is very important to us. Very important to us. So what I'd like you to do now is watch NASA ScienceCast, Earth's magnetosphere. And I'm going to take a time out. Go ahead and hit pause when you're done. We'll hit start again and we'll get started. Awesome, you're back. Exciting. All right, so that was really great. Now, when we think about us as a magnet, so the current theory, which is a pretty good one, is that our magnetism is coming from our core, you know, the solid metal inner core. It's a hypothesis because nobody can go down there and drill down and go, oh, I took a sample. You know, that's impossible. But our magnetic field does cause some amazing events to take place. And that's called the Aurora Borealis. Aurora Borealis and Aurora Australis in the southern hemisphere, Aurora Borealis in the northern hemisphere. And what I did is I included a couple video clips here of what the northern lights look like. And what's happening is incoming solar radiation strikes our ionosphere, and it excites electrons in the outer atmosphere. And the reality is this: people have been trying really hard to study to see if we can harness the energy that's going into this area. And if we could, it could power our world for the rest of eternity. But they're not there yet. So I'm going to take a couple minutes, watch Aurora Borealis, and then I really like the one from the International Space Station because it puts you above it. It's really cool. So I'm gonna hit pause. I have you hit pause, and then when we get done, pick it back up. Okay, you're back. It's exciting. So we're going on, and we're going to talk about gravity. Gravity is what causes all objects or all matter to be attracted in the universe. And you know, a lot of people talk about Sir Isaac Newton and him getting in the head, hitting the head with an apple as he's sitting under an apple tree, and actually, that's not exactly how it happened, and a lot of people made that story up. But there's some other things involved, and the law of gravitation that he came up with, or what he said, was that there's a force of attraction between two objects, and the larger the mass, the greater the attraction, and then the greater the distance, the less the attraction. So the closer an object gets, the greater the attraction. The greater the mass, the greater the attraction. And so Sir Isaac Newton came up with his law of gravitation. And what I'd like you to do is watch the BBC Gravity and the Apple and what on earth is wrong. So take a time out, push pause, watch that, and then when you're done, come on back. All right, we're back. Very cool. Isaac Newton, right? And it's the story of a comet, right? And how thankful we are that we have people who had great records back then. Okay, so what is weight? Well, I can tell you my scale lies to me every day, which it doesn't, but weight is gravity and the attraction or the force that's on any matter. So if you think about us, the further we get from the center of the earth, the less the force of gravity has on us. There's a column of air that goes right above us, and it's pushing us down, and we have this incredible pull on us by the earth. Now, the moon is a little bit different. It's smaller, and as a result of that pull, we're only 1/6 the weight that we are on the moon than we are on the earth. And I think that's pretty cool. So what's the difference between weight and mass? Well, weight is gravity's pull. Mass is how much material there is there, how much there is. And so our mass on the moon versus the earth does not change. But our weight does, because that's the difference of gravity's pull. And that measure is called a Newton. So let's review real quick. We'll take a time out here. We talked about the 3 characteristics of Earth's major zones. We explained how seismic waves have provided information about the Earth's interior. We've defined magnetosphere and what's going on there. And then we summarized Newton's law of gravitation. Guys, you guys did a great job today. Thank you so much for being awesome. Can't say thank you enough. And I hope you have a fantastic day.